Hello, welcome to our video series for Algebra 2 Accelerated. In this video we're going to be dealing with Chapter 1, Section 3, which is involving square roots. And we're starting with, for this video we're going to be doing example 2. And if there was not an example 3, that's because we decided to skip it for the distance learning. I might go back in and do it at some point if you're watching these videos at a later date, once we're back in class. Before I talk about the properties of square roots, which is the next piece of paper I'm going to work with, let's talk about perfect squares. And I made a list here of the first 20. This goes, obviously it goes on forever. So I have 1 to the second power equals 1, 2 to the second power equals 4, 3 to the second power equals 9. We call these squares because if I had, in geometry, if I had a square and say this side was 4 and this side was 4, then the area would be 16. So that's where we get the idea of square. That's why we use the word square when it comes to this. All right, and I'm not going to read through all these, but you can read them. The perfect squares are actually these numbers: 1, 4, 9, 16, 25, 36, 49, 64, all the way up to 400. On this piece of paper, if I kept going, 21 squared is actually, what, 421? Yeah, I think so. So, and then 22 squared, 23 squared, and you keep going, it would keep going. But we probably won't need to see anything more than, say, the first 20. There's a lot of discussion we can have about these. It's really, really interesting. Notice that each of these are increasing by an odd number, so plus 3, plus 5, plus 7, plus 9. And that has to go back to like the idea of what a square is. So if I have a 1 by 1 square, how many squares do I add to make a 2 by 2 square? And there's some other really interesting stuff in here. I don't really know if you need to memorize these. It would be good that you knew them. So if you had like a piece of paper or something where you wrote them down, if you're taking notes while you're watching the videos, feel free to pause it. I will take a picture of this and put it in the same Google Drive that the video's in, so you can look at it later if you want to, or you can come up with it by yourself. When we're physically in the same classroom, I usually divide everyone up and say, all right, you come up with these and then we'll write them down. It doesn't take very long. It's just a little bit of a multiplication exercise. But why am I talking about perfect squares when the lesson is about square roots? Well, the reason why is because if I take a number like 4 and I square it, I get 16. Going this direction, we say that you're using an exponent. But if I'm going back this direction, I say, what is the square root of 16? And that gives me my 4. Then I'm dealing with a radical, or like I said, a root, okay? And I know some of you know something called PEMDAS. I'll mention that later in a later video. But actually there's an R in there too. It's actually E and R. These two go together for exponents and radicals. That's an A, sorry. And you can also sometimes call this roots. These two operations are inverses of each other. So if I have 4 and I square it, I get 16. And if I take 16 and take the square root, I go back to 4. So all of these will tell me the square roots of the perfect squares. So for example, the square root of 169 equals 13. And the square root of 81 equals 9. Now there's a couple of other things I need to mention about square roots before we move on to like the properties. This right here with no sign in front of it, this is what we call the principal square root. And it's with an AL. I hope so. The principal square root is always the positive one because it goes back to this idea of geometry. All right. If I put a negative in front of it, like negative square root of 64, then that equals negative 8. It's the opposite of the square root of 64, so that's the opposite of 8. You're not going to worry about negatives in this section, but it will come up later. Sometimes I want both of them, and I put a plus or minus in front of them. You have probably already seen that. I don't need you to worry about that right now. In this case, everything we're going to be dealing with is positive if you don't see a sign, or it's negative if there's a negative sign in front of it. You're not going to see a plus or minus in this section. Okay? So that's how the square roots work. So the square root of 225 is 15, square root of 196 is 14, etc. You might notice that even though I went 1, 2, 3, 4, 5, I could have gone between 1 and 2, between 2 and 3. So I could have said something like, what's 2.5 squared? All right? Or going back the other way, what about between 1 and 4? What's the square root of 3? So these perfect squares have square roots that are going to be what we call rational. But the numbers that are between it, so 2, 3, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, all the numbers that I would count with, but not these perfect squares, those are going to have irrational roots. I don't need you to worry about irrational now. That's actually example 2, how to estimate irrational roots. For our purposes, for this section, we're only going to simplify. All right. So there's a lot of information out there, and I know you've got some experience with this. So I'm kind of like, I know I'm bringing up what not to do so that you don't panic or anything. Okay. And I know that kind of comes off as, but did he mention it? It's okay. It'll be all right. Again, you don't have to copy this. I actually stole it from the book. These are the 2 properties of square roots that we want to worry about. And I'm not going to quiz you over the names or anything. It's okay. All right, you got the product property and the quotient property, and they basically work the same way. You know how a moment ago I said exponents and radicals are inverses of each other? Multiplying and dividing are also inverses of each other. There's, when we get to order of operations, I'll say more about that. Just not in this video. All right, so the product property says that if, and actually it's kind of confusing the way they have it here. Usually we start with that side, we end up with that side. So the product property says, if I have the square root of 5, and I'm going to multiply that by the square root of, let's say, 7, that's going to be equal to the square root of 35, and vice versa. So if I went backwards, and I said, well, what's the square root of 8? Well, there's lots of things I can factor to equal 8. Is 1 times 8? That doesn't help. I can say square root of 1 times square root of 8. That's still 1 times the square root of 8. So I'm back at the square root of 8. I also have the square root of 4 times the square root of 2. That's another choice. This one's actually more interesting because, going back to this page, 4 is a perfect square. I know what the square root of 4 is. Square root of 4 equals 2, so I'd say that that's 2 times the square root of 2. This process right here is called simplifying the radical. So essentially, I'm using this product property to factor the number under the radical, to factor it into a perfect square, and I'll take the square root of that, and then whatever's left. So for another example, maybe I have square root of 75. So there's a couple things I can multiply. I can multiply to get 75. 1 times 75, 5 times 15. But the next one I would say is cool because it actually involves a perfect square. 75 is 25 times 3. So the square root of 75 would be the square root of 25 times the square root of 3. And since 25, going back to this other sheet right here, is a perfect square, simplified, this would be 5 times the square root of 3. So the idea of simplifying a radical is to see if you can factor this number into a perfect square times whatever else. If you can get a perfect square, that's great. In this example, 12 is 4 times 3, and 4 is a perfect square. So we would simplify this and get 2 times the square root of 3, right? Let's try this one. What about the square root of 30? Hopefully you guys can see that. I'll scoot up a little bit. We say, all right, well, 30 is 1 times 30 again. I'm going to write it down. 2 times 15, 3 times 10, and what, 5 times 6? So the square root of 30 would be the square root of 2 times square root of 15, square root of 3 times square root of 10. All those things are true. But notice that none of these are perfect squares. So this one cannot be simplified. So not every radical can be simplified. Only the ones that have a perfect square as its factor, as a factor. Okay? And usually, sometimes some of the numbers, there might be a perfect square that we see, and we can find out that there might actually be a bigger perfect square. Because if you go back to this, for example, see that 4 is actually a factor of 16. So if you notice the 4 is in there, but it's actually 16, that means there's going to be another 4 in there. So we always want to find the largest perfect square that's a factor. All right, so let me do a couple of examples for you. And these are examples from the book, and they are all different types of examples, all right, not just the simplifying that we were talking about. All right, let's look at example A. I've got the opposite of the square root of 50. We want to simplify this. Well, the negative sign right there is going to stay there. Nothing that's not going to change. I'm not multiplying it by negatives or anything like that. So this is still going to be negative. The square root of 50 is already a positive number. So the opposite of a positive number is going to be a negative number. I'm going to end up with a negative number. 50. Let's go back to my list of perfect squares. Are any of these factors of 50? Well, 1's always going to work, but it's trivial and it's not going to help, so skip it. 4, nope. 9, no. 16, no. 25, yes. 25 times 2 equals 50. So this is the opposite of the square root of 25 times the square root of 2. And the square root of 25 is 5. So this is negative 5 times the square root of 2. And that's the simplified form. Let's look at B. 49 and 81 are both on my list. 49 and 81. This is a perfect example of why, we will be using calculators. I'm not anti-calculator, but I've seen this a lot of times. People just drop that right in the calculator and they have no idea what they did. We're not trying to get an approximation of this. We're not trying to give me a decimal. I'm actually trying to simplify it. That's what the directions say. And notice that, going back to this sheet again, 49 and 81 are both on there. So instead of dividing and taking the square root, which you could do on a calculator, this actually becomes, because of the quotient property, this actually becomes the square root of 49 divided by the square root of 81. And that equals 7/9. Notice for this problem, for that problem, I know that you guys are, first time that you've actually started to watch Mr. Martin do any math. Notice I didn't put any equal signs in here. I didn't say this equals this equals this equals this. That's because technically that's right, but a lot of people use the equal sign incorrectly. So I use it very sparingly so that I only use it in certain situations. Like if you go back to this sheet, the square root of 81 does equal 9. And I've used it in different situations. But in this case, as I simplify, I'm not going to use equal signs. For C, these two, neither one of them is a perfect square. I could probably get something out of 18, but actually I'm going to multiply. 2 times 18 is 36. So this is the square root of 36, because 2 times 18, here's my equal sign, does equal 36. Maybe someday I'll tell you about other things we use the equal sign for, so why I'm always careful around it. All right, equals does not mean give me the answer. It just means two things have the same value. But back to this. Square root of 2 times square root of 18 equals square root of 36. And the square root of 36 is 6. That results in a perfect square. Finally, for problem D, it's bugging me that I didn't tab over this line up. Try to ignore that, okay? Finally, for part D, this 96 I don't know, square root of 96 I don't know, square root of 6 I don't know, but I can do this. I can go backwards from what I did here. So I'm going to combine these. This gives me the square root of 96 divided by 6. And I mentioned that with this problem, don't divide first. split it into different radicals because you know the square root of 49, you know the square root of 81. I don't know the square root of 96. I don't know the square root of 6. They're irrational. But I do know that 96 divided by 6, sorry, I lost my notes. 96 divided by 6 should be 16. So this is the square root of 16, which does equal 4. So notice that for this problem, that problem, and that problem, because we're showing different ways of doing it, I ended up without a radical, 6, 4, and 7/9. This is a rational number. It's just, it's a repeating decimal, but what I don't need is a decimal. This still has a radical in it because I only simplified out the square root of 25. I still had the square root of 2 left over in that. Okay, so in the next video, if you're following along doing them in order, I will be doing problems from the guided practice part in the back of the book.